And now in this lecture we'll find out the radius of the big circle. In the drawing we have a big triangle. Inside the big triangle we have two circles and a square. The radius of the small circle is equal to 1 unit. One side of the square is equal to 3 units, and our mission is to find out the radius of this big circle. Okay, so first of all we will define the vertex A. The vertex is point A. We'll define this vertex of the triangle as point B. We'll define this vertex as point C. We'll define the center of the small circle as O. We'll define the center of the big circle as P. We'll define the point of tendency of tangent BC with this circle as point Q. We'll define the point of tendency of tangent BC with the small circle as D. We'll define the touching point of the square with side BC as E. We'll define the second touching point of the square with BC as F. We'll define the touching point of the square with the circle as G. We'll define the touching point of the square with side AC as H. We'll define the touching point of tangent AC with the big circle as K. And here we will define the touching point of the small circle with the square as L. We will join points O and L together by a straight line. Point O is the center of the circle. Point L is the point of the circle itself. Therefore, OL is the radius of the small circle that is equal to 1. So R equals to 1. And we have rule number 1, that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So therefore we have the radius OL that is drawn to the point of tendency. Therefore this angle will be equal to 90 degrees and this angle will be equal to 90 degrees according to rule number 1. Likewise, we have the radius OD that is drawn to the point of tendency. Therefore this angle will be equal to 90 degrees and this angle will be equal to 90 degrees according to rule number 1. Likewise, we have the radius PQ of the big circle that is drawn to the point of tendency. Therefore this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. We know that all the angles inside the square are right angles, so this angle equals to 90 degrees, this angle equals to 90 degrees. We know that the side, all the sides of the square are equal to 3 units. So this angle equals to 90 degrees and this angle will be also equal to 90 degrees. And we also have here rule number 3. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So BC is one side of triangle ABC, therefore it is absolutely a straight line. So if we focus on the upper side of the straight line BC at point E, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have on the upper side of this 8.3? We have this angle that is equal to 90 degrees. So this angle must be equal to 90 degrees also. In order to complete the sum of the angles on the upper side of this 8.3 to 180 degrees, this angle must be equal to 90 degrees. Likewise, if we focus on the upper side of this 8.f, the sum of the angles must be equal to 180 degrees according to rule number 3. So this angle equals to 90 degrees. So this angle must be also equal to 90 degrees for the same reason according to rule number 3. Okay. So here, inside quadrilateral OLED, we have 1, 2, 3 right angles. Again, inside quadrilateral OLDE, we have 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So, inside quadrilateral LOED, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral LEOD as a rectangle. Quadrilateral LEOD is a rectangle because it has 4 right angles. Okay. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LOED, LO equals to ED. LO equals to ED. Okay? LO equals to ED. But here, LO equals to 1 unit. It is the radius of the circle, of the small circle. From this equation, 1 equals to LO equals to ED. We will derive that ED is also equals to 1 unit. ED equals to 1 unit. Likewise, according to the same rule, OD must be equal to LE. OD must be equal to LE. But OD equals to 1 unit. So we can write here that OD equals to 1 unit. And from this equation, LE equals to OD equals to 1. We will derive that LE is also equals to 1 unit. LE is also equals to 1 unit. But we know that edge E is one side of square GHFE. And we know that all the sides of the square are equal to 3 units. So if AG equals to 3 and LE equals to 1, LH will be equal to 3 minus 1, that is 2. Okay? And we also have here rule number 2. According to rule number 2, the lengths of 2 tangents from a common external point to a circle are equal. Here we have the common external point, point P. From the common external point, point P, we have tangent PA and tangent PB. And according to rule number 2, this rule, the length PA equals to PB. Okay, we can implement rule number 2 in our drawing, because in our drawing, if we focus on the common external point, point H, we define the touching point of side AC with this circle as point M. From the common external point, point H, we have 2 tangents to this circle. Tangent LL, tangent edge L, and tangent edge M. Tangent edge L and tangent edge M. And according to rule number 2, the lengths of those 2 tangents are equal to each other. That is to say, edge M is equal to edge L. But edge L is equal to edge M, according to rule number 2. I'll repeat again, edge L equals to edge M according to rule number 2. But we already found out that edge L equals to 2 units, so we can write here that edge L equals to 2, and from this equation 2 equals to edge L equals to edge M, we will derive that edge M is also equals to 2 units. Edge M is also equals to 2 units. Okay, edge M is also equals to 2 units. Likewise, if you focus at point C, point C is a common external point in relation to the small circle. From point C, we have two tangent to the circle. We have tangent CM and we have tangent CD. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, CM equals to CD. So if we define CM as X, then CD must be also equal to X because of the fact that they are equal to each other according to rule number 2. Okay? So in the next step, we will focus on the, here we know that in quadrilateral LOED, quadrilateral LOED is actually a rectangle because of the fact that it has 4 right angles. I already wrote it that quadrilateral LOED is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, LO equals to ED. LO is equal to ED. Okay? LO equals to ED. But we know that LO equals to 1 unit. So we can write here that LO equals to 1 unit, and from this equation 1 equals to LO equals to ED, we will derive that ED is also equal to 1 unit. ED is equal to 1 unit. So here we will focus on the right green triangle, triangle HCE. We will implement the Pythagoras theorem on the right green triangle, triangle HCE. In the right green triangle, triangle HCE, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT's evaluation from Pythagoras theorem, the hypotenuse is HC and the square of the hypotenuse is HC squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to HE squared plus EC squared. Okay. I'll repeat again. According to the Pythagoras theorem, in the right triangle HCE, HC squared equals to HE squared plus EC squared. So HC squared, what is the value of HC? HC equals to 2 plus x, therefore HC squared equals to 2 plus x squared, and it is equal to HE squared. HE equals to 2 plus 1, that is 3, so HE equals to 3, therefore HE squared is 3 squared, that is 9. plus EC squared. EC equals to x plus 1, therefore EC squared equals to x plus 1 squared. So in conclusion, we found out that according to equation number 1, 2 plus x squared equals to 9 plus x plus 1 squared. Here we will open the brackets on both sides of this equation, equation number 1, and we will get that according to equation number 1, 2 plus x squared equals to 2 squared, that is 4, plus x squared plus 2 times x is plus 4x, and it is equal to 9 plus x plus 1 squared equals to x squared plus 1 squared, that is 1, plus 2x. So here we have x squared on both sides of the equation number 1, so x squared will get cancelled. And what is left after we cancel x squared from equation number 1? In this side of the equation we have 4 plus 4x. In the other side of the equation we have 9 plus 1 is 10 plus 2x. So here we subtract from this equation number 1, and we get that according to equation number 1, 4x equals to 10 minus 4 is 6. 6 plus 2x. Here we subtract 2x from this equation number 1, and we get that according to equation number 1, 4x plus 2x is 4x minus 2x is 2x, and 2x equals to 6. Here we will divide this equation number 1 by 2, and we get that x equals to 3 units. So we found out that x equals to 3 units. So I actually can write down here that x equals to 3 units, and here also x equals to 3 units. Okay, so here we will join point C and O together by a straight line. We will join points O and M by a straight line. So here point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle, that is equal to 1. In the next step, we will prove that those two green right triangles are congruent to each other. Actually, the radius OM, it is drawn to the point of tendency, therefore this angle equals to 90 degrees and this angle equals to 90 degrees. So we will prove that the right green triangle, triangle OMC, is congruent to the right green triangle, triangle ODC. So why those two triangles congruent to each other? First of all, we know that DO equals to OM. They are both the radii of the circle, that is equal to 1 unit. In addition, we know that CD equals to CM equals to 3 units according to rule number 2. CD equals to CM equals to 3 units. And finally, CO is a common side that belongs to both triangles, so CO equals to itself. It's a common side that belongs to both triangles. Okay. So we actually proved the triangle OMC can go into triangle ODC according to side rule. So I write it down. Triangle OMC congruent to triangle ODC according to side rule. And from the fact that those two triangles can go into each other, we'll conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be also equal to each other. So if we define this angle as theta, then this angle must be also equal to theta because of the fact that those two angles are equal to each other. Okay? In the next step, we will join points C and P together by a straight line. We will join points P and K together by a straight line. Point P is the center of the circle. Point K is the point of the circle itself. Therefore, PK is the radius of the circle that is equal to capital R. In the next step, we will prove that the right big triangle, triangle PKC, is congruent to the right big triangle, triangle PQC. Actually, we have the radius PK that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So we'll prove, but before that, here we'll join points M and E together by a straight line. By joining points M and D together by a straight line, we created here triangle MDC. And here OC is angle bisector. OC is angle bisector of angle C. This angle C in triangle MDC. I'll repeat again. OC is angle bisector of angle C in triangle MDC. Why? Because angle bisector OC bisects angle C into two halves, each half equals to theta. Okay, so in the next step we'll prove that the big triangle, triangle PKC, the big right angle, is congruent to the big right angle, triangle PQC. So why those two triangles can go into each other? First of all, we just right now found out that PQ equals to PK. They are both the radii of the circle. PQ equals to PK. They are both equal to R. It is the radius of the big circle. In addition, according to rule number 2, if we focus on the common extreme point, point C, we have two tangents to the big circle from the common extreme point, point C. We have tangent CQ and we have tangent CK, and they are both equal to each other according to rule number 2. So here PQ is equal to PK. CQ is equal to CK. CQ is equal to CK according to rule number 2. Okay, CQ is equal to CK according to rule number 2. And finally, we have side PC that is a common side, it belongs to both triangles, so PC equals to itself. PC equals to PC, it is a common side that belongs to both triangles. So we actually proved that the two big right triangles can point to each other according to side rule. Okay, so write it down. Triangle PKC is congruent to triangle PQC according to side rule. And from the fact that those two triangles can point to each other, we derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. The two big triangles can point to each other, therefore those two angles must be also equal to each other because they are the corresponding angles in congruent triangles. So if one angle equals to theta, then the other angle must be also equal to theta. So we'll join points K and Q together by a straight line. So we actually found out that PC, line segment PC, the big line segment, is angle bisector of this angle, angle C. Angle C in the big triangle KQC. In triangle KQC. I'll repeat again. We actually proved that PC is angle bisector of angle C in triangle KQC. We actually found out that angle C has two angle bisectors, CO and PC. Okay, they are both bisect angle C into two halves. Each half equals to theta. Okay. So in the next step, we'll prove that the angle bisector CO passes through point P again. We'll prove that angle bisector CO of angle C passes through point P. Or in other words, we'll prove that points C, O, and P, they are all located on the same straight line. Okay, so our claim is that angle bisector OC passes through point P. I'll repeat again. It is exactly to prove that points P, O, C, O, and P, the 3 points are located on the same straight line. So our claim is that angle bisector OC passes through point P. We will prove the claim in a negative way. Okay. I'll repeat again. We will prove the claim that OC passes from point P in a negative way. That is to say, we will assume that CO doesn't pass from point P. Okay, so let's assume in a negative way that CO doesn't pass through point P. Okay, our assumption is CO doesn't pass through point P. And so if PO doesn't pass from point P, then we'll have two angles. Here we have angle DCO, that is equal to theta. Okay. So according to our assumption, we have angle TCO that is equal to theta. CO is the angle bisector. And the second angle that we will have, that if CO doesn't pass for point P, will be angle PCB. Repeat again. The second angle that we will have, that if CO doesn't pass from point P, is angle PCB. And here DC is part of BC. You can see here that DC is part of the straight line BC. Again, DC is part of the straight line BC. So we can say that DC is located on the same straight line that BC is located. Or in other words, we can say that one leg of each angle is a common leg, because they are both located on the same straight line. So the first leg of each angle is a common leg, because they are both located on the same straight line. While according to our assumption that CO doesn't pass through point P, it means that CO doesn't located on the same straight line that CP is located, because only of CO, if CO passes through point P, then CO will be located on the same straight line as CP. Otherwise, CO will not be located on the same straight line as CP. Okay, so therefore CP and CO, they are both located on different straight lines. Okay, CO and CP, they are located on different straight lines. Okay, so we have one leg is a common leg, and the other leg on both triangles are located on different straight line. Okay, the straight line CO doesn't located on the straight line as PC is located. So therefore, when we have one leg of the two angles that is a common leg, and the other leg is not located on the same straight line, it means that the two angles cannot be equal to each other, because when we have one leg that is a common leg, that is to say DC and BC is a common leg, then only if the second leg of the angle is also a common leg, is also located on the same straight line, only then the two angles will be equal to each other. Otherwise, those angles will be different angles. So if this angle is theta, then this angle will be equal to alpha. It makes sense, because if one leg is located on the same straight line, then the other leg must be also located on the same straight line in order that the two angles will be equal to each other. Otherwise, the two angles will not be equal to each other. So actually we found out that angle C has two angle bisectors that bisect it into two different halves. The angle bisector OC bisect angle C into two halves, that is theta and theta, while angle bisector PC bisect angle C into two halves that are alpha and alpha. But it is not possible. It is not possible. Why? Because, for example, if angle C is equal to 30 degrees, then any angle bisector will bisect it into two halves, that each half will be equal to 50 degrees, and only 15 degrees, and not any other angle. That is to say, each angle has only one angle bisector, or each angle will be bisected by two halves that always will be equal to each other. Okay, angle bisector, if angle C is equal to 30 degrees, then it means that any angle bisector will bisect it into two halves, that each half equals to 15, and not any other angle. So due to the contradiction that we found two different angle bisectors that bisected into two different halves, okay, due to the contradiction, is because we assume that CO doesn't pass from point P. Therefore, we'll conclude that our assumption was not correct, and we'll conclude that OC passes for point P. Okay? OC passes for point P. So here in the small right green triangle ODC, this small green triangle ODC, this angle equals to theta, this angle equals to 90 degrees, therefore the third angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, we will focus on the big right triangle, triangle PQC. On the big right triangle, this angle equals to theta. This angle equals to 90 degrees, therefore the third angle must be equal to 90 degrees minus theta for the same reason. Okay, so in the next step, we will prove that the right big triangle, triangle PQC, is similar to the small right big, small right green triangle, triangle ODC. So why those two green triangles are similar to each other? So first of all, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So here angle QPC, this angle in the right big triangle is equal to this angle, that is actually angle DOC. Repeat again, angle QPC equals to angle DOC, they are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, we have those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this angle is angle PQC in the big right triangle is equal to this angle that is actually angle ODC. I'll repeat again. Angle PQC equals to angle ODC. They are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle, angle theta, is a common angle that belongs to both triangles, so angle theta equals to itself, or we can define angle theta as angle PCQ is equal to itself. We can define angle theta also as angle OCD. Repeat again, angle PCQ equals to angle OCD. Actually, it means that angle theta equals to itself. Those are two different names for the same angle. It means that angle theta equals to itself as a common angle that belongs to both triangles. So actually we proved that the two right triangles can go are similar to each other according to angle similarity rule. So I write it down. We proved actually that triangle PQC is similar to triangle ODC according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will conclude actually that PQ in the big right triangle over OD in the small right triangle is equal to QC in the big right triangle over DC in the small right triangle. Repeat again. We'll conclude that here PQ over OD equals to QC over DC. So here what is the value of PQ? PQ is the radius of the big circle that is equal to capital R over OD. OD is the radius of the small circle that is equal to 1 unit. What is the value of QC? QC equals to 3 plus 1 plus 3, that is 7, plus QF. So we substitute QC by 7 plus QF over DC. What is the value of DC? DC equals to X, that is equal to 3. So we substitute DC by 3. So in conclusion, I found out that according to equation number 1, R equals to 7 plus QF over 3. So here we will multiply this equation number 1 by 3, and we will get that according to equation number 1, R equals to 3R equals to QE plus 7. I write it again. 3R or QE. Here we subtract 7 from this equation number 1, and we get that according to equation number 1, QE is equals to 3R minus 7. Okay, QE is equal to 3R minus 7. So we can write in the drawing that QE, here QE is equal to 3R minus 7. Okay. So here we are looking for the value of the radius of the big circle, and actually the value, the length of the radius of the big circle can be equal, can be less than 3 units, it can be equal to 3 units, or it can be greater than 2 units. So we'll examine each case in order to find out the length of the radius of the big circle. So case 1 is what happens is if the radius of the big circle is less than 3 units. Okay? If the radius of the big circle is less than 3 units, then it could be equal either to 2 or 1. Only 2 possibilities. There are no other possibilities because of the fact that radius is a length, and a length must be a positive number. Okay? If R equals to 1, actually, when we say that R is less than 3 units, we have infinite possibilities for the value of R, of course. But we will check for the value of R that is equal to 1 and the value of R that is equal to 2. I repeat again, there are another infinite possibilities for the value of R if R is less than 3. But we will examine only 2 possibilities, and from the 2 possibilities we will conclude for the other infinite possibilities. Okay? So if R equals to 1, then we get that according to equation number 1, QE is equals to 3R minus 7 we'll substitute R by 1 because R equals to R and 1 according to our assumption, and we get that QE is equals to R is 1, so 3R is 3 minus 7. 3 minus 7 is minus 4. So we found out that QE is equal to minus 4. And because of the fact that QE is a length, here QE, actually it is QF. QF is equals to 3R minus 7. So in QF, so I found out that QF equals to minus 4, but QF is a length, and as a length it must be a positive number. Okay? But now we can understand that if R is equal to any other infinite possibilities that we have from 1 to 0, let alone that that QF will be a negative number. Okay? So we'll cancel out all the infinite possibilities that we have for R that is 1 or less than 1. Okay? So if R equals to 2, then again we have equation number 1 that QF is equals to 3R minus 7. So R equals to 2, so we substitute R by 2 in equation number 1, and we get that QF is equals to 3 times 2 is 6, and 6 minus 7 is minus 1. So QF is equal to minus 1. Again, QF is a negative, and we know that QF is a length, and as a length it must be a positive number, so R cannot be equal to minus 1, it must be a positive number. Okay, and the idea here that is that if R is less than 3, then in this equation we will get that QF is a negative number. Actually, if R is 2, then we got a negative number, and here, so R cannot be equal to less than 3 units, because here we get that QF will be a negative number, and QF is a length, it must be a positive number. So in the next step we'll examine the possibility, so R cannot be less than 3 units. Okay. Actually, if R equals to 2.5, then we'll get that QF is indeed a positive number. So if R equals to 2.5 units, then we get that QF is equal to 3 times 2.5 is 7.5, minus 7 is 1/2. Okay, QF equals to 1/2. But here we'll get that QF equals to 1/2, and here we have so actually if R equals to 2 units, then QF is a positive number, it is equal to 1/2, but here we get a contradiction. Okay, so we will examine the possibility that R equals to 3 units. The second case, case 2, is that if R equals to 3 units. So actually I will show you that we'll get here a contradiction if R equals to 3 units, and we will arrive to the same conclusion about R equals to 2.5 units. Okay, so if R equals to 3 units, then we have a circle that is equal to 3 units. Actually, I want to return to the case 1 if if R is less than 3 units. Then again in case 1, if R is less than 3 units, then we will have a radius that is less than 3 units. Okay, and you know that the square is equal to 3 units. This is the radius. So here we have a radius that is greater than 0 but less than 3 units. So, and from this proof we can conclude for other infinite possibilities that we have for R that is less than 3 units. Actually, according to my proof, actually it is a little bit problematic, because then I proved it for R equals to 1, and I proved it for 1 equals to R equals to 2, but we have another infinite possibilities that I didn't prove it. So here we'll take R that is less than 3 units. So here R is less than 3 units, and here, according to rule number 1, the angle here is 90 degrees. And here, according to rule number 1, this angle, it is also equal to 90 degrees. And we have here a square that is equal to 3 units, therefore it will be a little bit higher than the radius here. Here it will be a little bit higher than the radius. So here, this is equal to 3 units. This is equal to 3 units. All the angles inside the square are right angles. This is also equal to 3 units, so those angles are right angles in this square. So here, this is angle P, this is angle Q, this is angle G, this is angle F, point F, this is point E, this is point H. So here we'll focus on the upper side of the straight line QE, QE is part of side BC, therefore it is absolutely a straight line. So in the upper side of the straight line QE at point F, the sum of the angles must be equal to 180 degrees according to rule number 3. So this angle equals to 90 degrees, so this angle must be also equal to 90 degrees in order to complete the sum of the angles on the upper side of QE at point F to 180 degrees. This angle must be equal to 90 degrees. So actually, inside quadrilateral P, we define this point as, so this point is point G. So inside quadrilateral P, G, Q, F, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Okay. So here, quadrilateral P, G, Q, F has 4 right angles, therefore quadrilateral P, G, Q, F is a rectangle. I write it down. Quadrilateral P, G, Q, F is a rectangle because of the fact that it has 4 right angles. Okay. As we know that the opposite sides of a rectangle are equal to each other. That is to say, PG is equal to QF. PG is equal to QF. PG is equal to QF. But we know that PG equals to R. And from this equation, R equals to PG equals to QF. We derive that QF is also equals to R. From one side, QF equals to R. From the other side, QF equals to 3R minus 7. According to equation number 1, it is equals to 3R minus 7. Okay, so actually regard that R equals to 3R minus 7. Okay, here we subtract R from this equation and we get that 0 equals to 3R minus R is 2R. Minus 7, we'll add 7 to this equation and we get that 7 equals to 2R. 7 equals to 2R. We'll divide this equation by 2 and we'll get that R equals to 7 over 2, that is 3.5 units. Okay, so according to our assumption, R is less than 3 units. But here we found out that R is equal to 3.5 units. It is a contradiction. That is to say, R cannot be less than 3 units. Here we have a real proof that R cannot be less than 3 units. Because here R can be equal to infinite numbers between the values that is less than 3 until 0. Okay, so all the values, all the infinite values from that is a little bit greater than 0 and less than 3 will have a contradiction with the fact that R equals to 3.5. Therefore, it is a good proof that R cannot be equal to, cannot be less than 3 units. Okay? Because we have a contradiction that we found out that R is equals to 3.5 units. Okay? In the next step, we will will examine the second case, that R equals to 3 units. Okay, so if R, this is case 2, if R equals to 3 units. So now it is enough that we'll show that R have another value other than 3 units, and we'll get a contradiction. While in the previous proof that R cannot be less than 3 units, we actually have to prove it for R that is less than 3 units, and we have the infinite possibilities. Okay, so it is not good to prove only for 1 or 2 as I did. Okay, so here we have case number 2, that R equals to 3 units. So if R equals to 3 units, then we have a circle with a radius of 3. R equals to 3 units. Actually, if it is given us the question, if it was given us in the question that R is a natural number, then my proof is true, because the only 2 natural numbers that we have that are less than 3 units are 1 and 2. But here it is not given us the question that R is a natural number. Therefore, when you have to prove that R is cannot be equal to less than 3 units, you have infinite possibilities that you have to cancel. And it is not enough to prove only for 1 and 2. Okay, so here R equals to 3 units. And we know that the square, one side of the square is also equal to 3 units. this angle equals to 90 degrees according to rule number 3. So actually, inside quadrilateral PGQF, we have this angle actually equals to 90 degrees according to rule number 1. We have the radius PG that is 1 to the point of tendency, therefore this angle equals to 90 degrees. So inside quadrilateral PGQF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So, inside quadrilateral PGQF, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So, we relate quadrilateral PGQF as a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, PG is equal to QF. But PG equals to R, therefore QF, PG equals to R, that is equal to 3, of course. So you can find out that, so if PG is equal to 3 units, then QF must be also equal to 3 units. Okay. Likewise, we know that PQ equals to GF and PQ equals to 3, therefore GF is also equals to 3. So anyway, GF is equals to 3 because it is a square that one side of it is equal to 3 units. So here, from one side we found out that QF equals to 3 units. From the other side, it is equal to 3R minus 7. So QF equals to QF. QF equals to QF. So 3 equals to 3R minus 7. Okay. So here we will add 7 to this equation and we will get that 3R is equal to 10. 3R is equal to 10. We divide this equation by 3 and we get that R equals to 3.333 or 3/3. 3/3. So we have here contradiction because according to our assumption R equals to 3 and we got to the result that R equals to 3.333. So we have a contradiction and therefore we can conclude that R cannot be equal to 3 units. R cannot be equal both to 3 and 3.33, therefore R equals to 3 units is not possible. So we left only with the third case, that R is greater than 3 units. So we have case number 3, that R is greater than 3 units. So if R is greater than 3 units, then we know that the radius of the circle is greater than 3 units. So here we have a circle now that the radius of the circle R is greater than 3. So here R is greater than 3. Therefore, we get that R is higher than the square that is equal to 3 units. So here we draw the square a little bit shorter than the radius, because r is greater than 3. The center of the circle is at point P. We have here point Q. Those two angles are equal to 90 degrees. Then this angle equals to 90 degrees according to rule number 3. Here, GHFE. We will join, actually, from point G, we will draw perpendicular on the radius PQ. I repeat again, from point G, we will draw perpendicular on the radius PQ. So here, this angle equals to 90 degrees, and this angle will be equal to 90 degrees. According to our construction, we will define the touching point of the perpendicular from point G and PQ as T. So inside quadrilateral TGQF, we have 1, 2, 3 right angles. And look at again, inside quadrilateral PGQF, we have 1, 2, 3 right angles. Therefore, here the fourth angle must be also equal to 90 degrees. So know that GF is one side of the square that is equal to 3 units. So inside quadrilateral TGQF we have 4 right angles. So we relate to quadrilateral TGQF as a rectangle. Quadrilateral TGQF is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. Okay, so here we get that GF equals to TG. GF equals to TG. GF is equal to GF equals to TQ actually. GF equals to TQ. But GF equals to 3 units, so we can write here that GF equals to 3. And from this equation 3 equals to GF equals to TQ. We derive that TQ is also equals to 3 units. And TQ equals to 3 units. Here we join points P and G together by a straight line. Point P is the center of the circle. Point G is the point of the circle itself. Therefore, PG is the radius of the circle that is equal to R. What is the size of PT? It is very easy to see from the drawing that PT equals to PQ minus TQ. Again, PT is equal to PQ minus TQ. So PT is equal to PQ, that is capital R minus TQ that is 3. So in conclusion, found out that PT equals to capital R minus 3. And according to the rule that the opposite sides of a rectangle are equal to each other, we get that QF is equal to TG. QF is equal to TG. But we have already found out that QF equals to 3R minus 7. QF equals to 3R minus 7. So we can write here that QF equals to 3R minus 7. And from this equation, 3R minus 7 equals to QF equals to TG. We will derive that TG is also equals to 3R minus 7. TG is equal to 3R minus 7. So you can write here that TG equals to 3R minus 7. Now we will implement the Pythagoras theorem on the right green triangle, triangle PTG. Okay. So here I will copy the right triangle, triangle PTG in a new page, and we'll implement the Pythagoras theorem on the right green triangle, triangle PTG. So this is the right triangle, triangle PTG that I copied from the original drawing. We have already found out that PT equals to capital R minus 3, TG equals to 3R minus 7, and the hypotenuse PG equals to capital R. So here, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, the hypotenuse is PG, therefore the square of the hypotenuse is PG squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to PT squared plus TG squared. Okay, so here PG equals to R, therefore PG squared is R squared, and it is equal to PT squared. PT equals to R minus 3, therefore PT squared equals to R minus 3 squared plus TG squared. TG equals to 3R minus 7, therefore TG squared equals to 3R minus 7 squared. Here we'll open the brackets on both sides of this equation, equation number 1, and we get that according to equation number 1, R squared equals to R minus 3 squared is R squared plus 3 squared, that is 9, minus 2 times R times 3 is minus 6R, plus 3R squared is 9R squared, plus 7 squared is 49, minus 2 times 3 is minus 6, and minus 6, actually it is minus 2 times 3 is minus 2 times 3 is 6, and 6 times minus 7 is minus 42R. Okay. According to the algebraic identity, that a plus b square equals to a square plus b square minus 2 times ab. Okay. So here we have r square on both sides of the equation, so r square will get cancelled. What is left from equation number 1 after we cancelled r square? In this side of the equation we have 0, that is equal to 9 plus 48 is 58, and minus 6r minus 48, 2r is minus 48r, plus 9r squared. So we have here the quadratic equation 9r squared minus 48r plus 58 is equal to 0. Okay, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. A, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to a special formula for x, that x is equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, the coefficient a equals to 9, the coefficient b equals to minus 48, and the coefficient c equals to 58, and the variable that we are looking for is r, so x equals to r. So we'll put the values that we found in the solution for the quadratic equation, and we'll find out the values of r, that is the values of the big circle. So here we'll get that x is equal to r, so r equals to minus b, b is minus 48, therefore minus b is minus 48, that is plus 48, plus minus square root of b squared. So this is it is actually 48 square, that is 2304, minus 4 times a is 9, times c is 58, over 2a. A is 9, so 2a is 18. So in conclusion, we found out that r, the radius of the big circle that we are looking for, is equal to 48 plus minus square root of 2304, minus 4 times 9 is minus 36, and minus 36 times 58 is minus 2088. Minus 2088 over 18. So we get that r equals to 48 plus minus 2304 minus 2088 is 2016. So inside the root we left only with 216 over 18. And here r equals to 48 plus minus the square root of 216 is 14.6969 over 18. So here we will have two solutions that are possible for R. The first solution is that R equals to 48 minus 14.6969 over 18. So R equals to 48 minus 14.6969 is equals to 33.3031 over 18, and 33.3031 over 18 is 1.85. So we found out that R equals to 1.85, that is less than 3 units, and we have already found out that R cannot be less than 3 units. So this solution is the correct solution. We cancel this solution, and we left only with the second solution from the quadratic equation, that R equals to 48 plus 14.6969 over 18. So R equals to 48 plus 14.6969 is 62.6969 over 18, and 62.6969 over 18 is equals to 3.483 units. So we found out that the radius of the circle is greater than 3 units. That is absolutely possible. R cannot be equals to less than 3 units, so R cannot be equal to 3 units, but it is absolutely can be equal to 3.483 units, that is greater than 3 units. So finished with the question. In the next step, I'll summarize the lecture. So we have the drawing a big triangle. Inside the big triangle we have two circles at the square. You know that the radius of the small circle is equal to 1 unit, the radius of the square is equal to 3 units, and our mission is to find out the radius of the big circle. Okay? So here in this question we use 3 rules. We have rule number 1, that we use the lots. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So we have here tangent AB to this circle at point M, and tangent AB is tangent to this circle as point M. Point M is the point of tendency, and we have the radius OM that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. And we have also rule number 2, that the lengths of two tangents from a common start point to a circle are equal. We have the common start point, point P. From the common start point, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, this rule, tangent PA equals to tangent PB in its length. And finally, we use a lot also rule number 3, that the sum of the angles on one side of the straight line is equal to 180 degrees. We have here the straight line CD. If we focus on the upper side of the straight line CD at point O, here the sum of the angles must be equal to 180 degrees. So here That is to say, alpha plus beta equals to 180 degrees. So use those three rules a lot in the question, and we arrived to this drawing. Here we know that quadrilateral LOED is 4 right angles, therefore it is a rectangle. Therefore, in rectangle LOED, we know that side LO equals to side ED, but we know that LO is the radius of the circle that is equal to 1, so we can write that here that LO equals to 1, and from this equation 1 equals to LO equals to ED, we derive that ED is also equals to 1. Here ED equals to 1. Likewise, we have here we use then rule number 2 at point H. From the current standpoint point H, we have two tangents to the circle, tangent edge M and tangent L, and tangent edge L, tangent edge M and tangent edge L, and according to rule number 2, edge M equals to edge L equals to edge M, but we have already found out that edge L equals to 2, so we can write here that edge L equals to 2, and from this equation 2 equals to edge L equals to edge M, we derive that edge M is also equals to 2. Here edge M is also equals to 2. Okay, edge M equals to 2. Likewise, then we focus on the common point C. From the common point C, we have two tangents to the circle, tangent CD and tangent CM, and according to rule number 2, they are equal to each other. That is to say, CD equals to CM. Here, CD is equal to CM. Here we have, actually here we have tangent CM is equal to tangent CD, so here CM equals to CD. So if CM equals to X, then CD must be also equal to X. Okay. And then we return to the rectangle LOED that has 4 rectangles, and we know that OD is equal to LE. Here, and ED is equal to LO. ED is equal to LO, but we know that ED LO is the radius of the circle that is equal to 1, and from this equation 1 equals to LO equals to AD, we will derive that ED is also equals to 1. Okay. Then actually proved, we know that in rectangle LOED, OD equals to LE, OD equals to LE, but OD equals to 1, it is the radius of the circle, and from this equation 1 equals to OD equals to LE, we derive that LE is also equals to 1. So we actually found out that quadrilateral LODE is a square. Okay, then we have actually Then we joined points C and O together by a straight line. We joined points O and M together by a straight line. Point O is the center of the circle. Point M is the point of the circle itself. Therefore, OM is the radius of the circle that is equal to R. Then we proved that those two triangles can go into each other according to side rule. Here, the O equals to MO equals to R. CD equals to CM equals to 3 units according to rule number 2, and CO equals to CO. It is a common set that belongs to both triangles. From the fact that those two triangles can go into each other, we concluded that those two angles are equal to each other. So if this angle equals to theta, this angle must be also equal to theta. And then actually we join points M and D together by straight line. OC is the angle bisector of angle C. Bisects angle C into two halves, theta and theta. Then we proved that those two right triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we concluded that those two angles are equal to each other. So if one angle is theta, then the other angle must be also equal to theta. Then we have claimed that CO passes through point P. Or in other words, points C, O, and P, they are all located on one straight line. And before that, we actually concluded that CO is the angle bisector of angle C, and PC is also the angle bisector of angle C. And now our claim is CO passes through point P. Actually, we proved it in a negative way. We assumed that CO doesn't passes through point P. Okay, if CO doesn't passes at point P, then we will have this angle C OCD that is equal to theta, and we will have angle PCB that is equal to alpha. Why? Because here DC is part of BC. Therefore, they are absolutely located on the same straight line. Okay, so BC and DC, they are located on the same straight line, while if CO doesn't passes for point P, it means that PC and OC are not located on the same straight line. So if we have one leg that is a common leg, that is BC and DC are a common leg, because they are located on the same straight line, and the other leg is not located on the same straight line of both angles, it means that this angle can never be equal to the other angle, because we have one common leg and the other leg that is not located on the same straight line. So we have two different lines. For OC is not located on the same straight line as PC, therefore angle theta and angle alpha are two different angles. Otherwise, the only way that those two angles will be equal to each other is that OC will be located on the same straight line as PC. But according to our assumption, OC doesn't located on the same straight line as PC. Therefore, those two different straight lines, and therefore angle theta is not equal to angle alpha. So we actually found out that angle C is two angle bisectors that bisects it into two different halves. The angle bisector OC bisects it into theta and theta, then angle bisector PC bisects it into alpha and alpha. And this is a contradiction. Okay, why? Because if, for example, angle C is equal to 30 degrees, then any angle bisector will bisect it into two halves, that each half equals to 50 degrees and 50 degrees, and not to any other angles. Therefore, angle C should have only one angle bisector that bisects it into two halves, and not another angle bisector that bisects it into another halves. And so, due to our assumption that CO doesn't pass through point P, we arrive to a contradiction, and therefore we conclude that our assumption is not correct, and therefore OC passes through point P. Here OC passes through point C. So OCP are located on one straight line. Then we proved that triangle PQC is similar to triangle LEC, and from the fact that the two triangles are similar to each other, we will conclude that PQ over OD equals to QC over DC. PQ is R, OD is 1, QC is 7 plus QF, and DC is 3. So here we multiply this equation by 3, and we got that R equals to QE plus 7. Okay, then we have actually the radius of the big circle could be less than 3 units, it could be equal to 3 units, and it could be greater than 3 units. So we examine each case. If the radius is less than 3 units, then we actually get to a contradiction. Why? Because here, if the radius is less than 3 units, then we will have here this quadrangle PGQF is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, PG is equal to QF. But PG from one, so PG equals to QF, but QF it is equal to 3R minus 7 according to equation number 1 from one side, but because of the fact that PGQF is a rectangle, it means that PG equals to QF. And if PG equals to R, then QF must be also equal to R. So from one side, QF equals to R. From the other side, QF equals to 3R minus 7. So we found out that R equals to 3R minus 7. We subtracted R from this equation. We got 2R minus 7 equals to 0. Then we added 7 to this equation, and we found that 2R equals to 7. We divided this equation by 2, and we found out that R equals to 3.5 units. Okay, so our assumption is that R is less than 3 units, and we got to a result that R is equal to 3.5 units. It means that all the infinite possibilities that we have for R that is less than 3 units are not correct, because we found out that R is equal to 3.5 units. So we have a contradiction, therefore R cannot be less than 3 units. Then we examine the possibility that R is equal to 3 units. If R equals to 3 units, again we will have here a quadrangle PGQF, and here we know that in quadrangle PGQF we have 4 right angles, and therefore quadrangle PGQF is a rectangle. That is to say, GF equals to PQ, and GF equals to 3, therefore PQ is also equals to 3. Likewise, PG equals to QF, because the opposite sides of a rectangle are equal to each other. Okay, so here So if PG equals to QF, it means that PG equals to R, then QF is also equals to R. And R equals to 3 according to our assumption. So here we get that 3 equals to 3R minus 7, because for one side QF equals to 3 units, and from the other side we already found out that QF equals to 3R minus 7, therefore 3 equals to QF equals to QF, that is to say 3 equals to 3R minus 7. We added 7 to this equation and found out that 3R equals to 10. We divided this equation by 3 and found out that R equals to 3.333. That is a contradiction. According to our assumption, R equals to 3 units. So due to the contradiction, we actually can conclude that R cannot be equals to 3 units. Then we have the first case, that R is bigger than 3 units. If R is bigger than 3 units, we get here quadrilateral TGQF, that is a rectangle, and therefore QF is equal to TG, but QF equals to 3R minus 7, therefore TG will be also equal to 3R minus 7. Likewise, we know that the opposite sides of a rectangle are equal to each other, that is to say GF equals to TQ, but GF equals to 3, therefore TQ will be also equal to 3. We join from point G, we go perpendicular on PQ, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. Here, we join points G and P together by straight line. Point P is the center of the circle, point G is the point of the circle itself, therefore PG is the radius of the circle. What is the value of TP? TP is PQ minus TQ. That is to say TP equals to PQ, that is R, minus TQ, that is 3. So in conclusion, TP equals to R minus 3, and there TG equals to 3R minus 7, and the product of PG equals to R. So we implemented the Pythagoras theorem on the right green triangle, triangle TPG. In the right green triangle, triangle TPG, actually we have here in the right green triangle, triangle TPG, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say PG square equals to TP square plus TG square. PG equals to R, therefore PG square is R square. PT equals to R minus 3, therefore PT square is R minus 3 square. And TG equals to 3R minus 7, therefore TG square is 3R minus 7 square. We solved this equation and we arrived to two solutions. It is a quadratic equation. We have here two solutions that are possible. The first solution for a quadratic equation for R is that R equals to 1.85, but we have already found out that R cannot be equal to 1.85 because R cannot be less than 3 units, and 1.85 is less than 3 units, therefore we cancel this solution, and we have the other solution for R, for the quadratic equation, that R is equal to 3.483 units. So here R is greater than 3 units, therefore it is absolutely a correct solution. So in conclusion, found out that the radius of this circle, of the big circle, is equal to 3.483 units. Okay, the radius of this big circle is equal to 3.483 units. Okay, thank you very much.